All right, we're going to finish up this lecture on Chapter 45, Unit 45, and the second 132M110B, and we're going to finish where we had left off. So, in the previous class, we had talked a little bit about balance point and capacity of the systems and kind of where the heat pump should be shutting off and switching to a second fuel source due to capacity. We talked a little bit about a couple of balance points, so one of them being the thermal balance point that's shown in this image, as well as an economic balance point. And typically the thermal balance point is always the one that we end up having to deal with. In this particular slide, for example, we were talking about the heat pump and a heat mode, and specifically some of the main parts and pieces. So one of them that we had was the components that were on the heat pumps. We always expect to see, and using you have to have the two coils, one of them being the indoor coil, one of them being the outdoor coil. You've got to have a compressor. You almost always have an accumulator. The metering device there's going to be what they call an outside metering device and an inside metering device. You'll have two separate metering devices most often. There will have to be the check valves in the metering devices. If they are, depending on the operation, but there's got to be some type of a valve or a check valve. And then, of course, a bi-flow filter dryer and a reversing valve is what typically has to happen on all of these heat pumps. So where we left off is we were just starting to talk a little bit about the reversing valve, and some people call that kind of the heart of a heat pump because it plays such a key role in the operation of the unit. Now, the reversing valve that we use on a heat pump it's going to determine the function, whether it's, are you doing heating or are you doing cooling. So it's determining the function of the indoor coil operation or function. So typically most heat pumps will get energized they will energize their reversing valve in the cooling position, and they will de-energize as a default in the heating mode. There will be 4 pipes on a reversing valve. One of the 4 pipes will always be by itself, and that's always the discharge line is what that one ends up being. There will be another one that is the suction, which will be the opposite of that. That one will be that will always be directly opposite of that, and then there'll be 2 other ports that will switch either on the far right or the far left, and they will go to the indoor and outdoor coils is how they're going to do that. So we'll take a look at that application. So on this particular one, we're showing a reversing valve drawn in the cooling mode, and you'll notice that from the compressor, my discharge is always going to go to that one all by itself. So if you look at this particular reversing valve image, you'll notice that the sole port is going to be the discharge line, and that's always the one that will always happen. Directly opposite of that will go to the suction gas going back to the compressor, and then oftentimes there will be an accumulator, and we'll see more pictures coming up a little bit later that usually that accumulator is just prior to the compressor. Whether it's switching from indoor coil to outdoor coil is really determined it's dependent upon the mode. The other thing that you have to have is you've got to have at least somewhere in that 75 to 100 psi differential to create the movement of the reversing valve. So typically what happens is most all reversing valves are what they call pilot operated, and so what they'll do is they'll energize a little valve that will take a tiny amount of refrigerant, and then it'll pressurize one side or the other. So that little solenoid valve is really just kind of creating a movement, not really shifting the valve, but it's allowing the pressure that's the reversing valve sees to actually push the valve over one way or the other. So that's really the key component to its operation. Now in this particular slide, I'm going to animate this one here so you can see what's going on with it. And on this particular one here, we're showing a compressor operation. So we're going discharge line. We are sending that directly to that single lone port, and then we're going to the outdoor coil. So right now we are in the cooling mode in this particular case. When we reverse it and go into the heating mode, just notice how what the change will occur on. So on this one, that one would now redirect that gas and now send the hot gas that the compressor was making, and it was sending that to the indoor coil. That'll be inside your building providing heating. Then of course the outdoor coil is now going to act like an evaporator, and that's going to pull the heat out and obviously send that directly back into there. So really that's kind of the operation, or the, what it's doing when they talk about it redirecting the flow. That's what has to happen. Okay, this is another little image, a very good image showing a heat pump in a heating mode, and if you look at the arrows kind of tell the story a little bit. On this one, we're going to leave on this compressor on the discharge line, which is all by itself. You'll notice that we're de-energized in this picture, and it's showing the reversing valve. And of course, we're going to redirect or direct that flow to the indoor coil because we are in the heating mode. And of course, that's going to give the heat to the inside of the building. Now, of course, there's going to be let's call it the inside TXV or an inside metering device. But in this case, we're showing a TXV, and this one here is the check valve. Most all modern TXVs that are used for heat pumps, this check valve is actually going to be built in to this device as an integral part. For the sake of doing this image, it's easier to show it as a separate part. But in real life, most of these are going to be built into the TXVs. So we're going to redirect or direct this indoor coil, the hot gas, which will now have been condensed, and we should be a liquid. We're going to send that and bypass the check valve, or go through the check valve, is bypass the TXV, and then we're going to send that through the biflow filter dryer, where that will filter the flow sufficiently in both directions without sending the whatever you filtered out when you're going into kind of almost like a reverse mode. So it's in some modes it's going to go one way, and the other mode it goes the other way, but it has to filter it and not send that particles out. Now in this particular one, the check valve is closed, you'll notice, and it will not let the flow through here, and it has to go through the TXV. So this will now be the outdoor TXV, the outdoor metering device. Now in our lab systems, we're going to have some will be TXV and some will be fixed orifice. So it just depends on the manufacturer and how they wanted to do it. And in this particular case, we're showing the metering device, which will send and drop the pressure and temp down. This outdoor coil will now act as an evaporator. This indoor coil will act like a condenser. Okay. And then of course we go through the coil, and we hope that the TXV did a good job controlling the flow, and we hope that this is all gas on that side in those lines, and we hope that it's slightly superheated a little bit. And of course we go directly into here, and we go right back into the accumulator, which is shown over here, and then right back into it, and we start the process over and over again. So now we go into the cooling mode. Now in this cooling mode, you'll notice how the reversing valve has redirected the hot gas to the outdoor coil, which will now act like the condenser in this case, and this side will act like an evaporator. And of course we send the hot gas. Notice how the direction has changed. in the previous slide, we were showing that the flow, whoops, let's go back, there we go. In the previous slide, we were showing the direction going in this particular manner into the coil, and then when we go to the cooling mode, notice how the direction has now changed. So now we're actually sending it the opposite way, which thus the reason for the bi-flow filter dryer. And of course, this check valve now is going to open, and so that basically means that this metering device assembly that we're showing right here really has to be unrestricted. So there should be very, very little pressure drop in that at all. It would really only be that of the check valve. And of course, we go through the bi-flow filter dryer. We go directly. You'll notice how the check valve is stopping it, and it says nope, you have to go through the meter device. So now this indoor coil which is now the evaporator indoor coil, has to now. This is going to now be your low pressure, low temperature saturated liquid vapor mix, and then of course this will act. It has to absorb heat. So just like any cooling system. So again, very, very similar operation to a normal cooling application. This particular image, I'm showing you a heat pump, like a job site informational sheet, and just showing. This is one example of one where we're showing, temperatures. You'd have to identify, what are the problems, or are you in the heating mode, are you in the cooling mode? What's your entering and leaving conditions in the indoor coil? Notice how the terminology they're using is indoor coil, outer coil. We're identifying, give me the pressures and the reversing valve, and they're just identifying a lot of the details and allowing you to go in and take these temps to, so liquid line temp here, liquid line temp here, before and after the filter dryer. What's the liquid line temperature prior to the coil? There's a lot of different details that they want to know so that we can identify if there's any particular problems with the system. And that's fairly typical in testing operation. And obviously, a lot of these we want to know if it's, is it liquid, is it vapor, is it superheated, is it subcooled, and is it, giving us that capacity of what we're looking for. There is another term that we had looked at. The last class we had talked a little bit about efficiencies, and in this particular slide we're looking at something called a coefficient of performance. And in the coefficient of performance, it's essentially a calculation that looks at the ratio of the BTUs that you are getting out of a system by the BTUs that you're putting into a system. And of course, the input can be converted into BTUs. Input's always going to be electrical energy, and we can convert that electrical energy input into BTUs by looking at how many kilowatts of energy that a person uses to create that heat and you can multiply those kWs times a factor of 3,413 BTUs, which is the conversion for kilowatts of energy to BTUs to kilowatts of energy to BTUs. So a kW of energy on this heat pump with a coefficient of performance at 2.5 would give you 2.5 times the 3413, or 8533 is what it would end up using. And that was, again, for assuming you were just using 1 kW. So it would be whatever the kilowatts of energy you're using. If you get a COP of 2.5, it's whatever that calculation of watts times the BTUs times 2.5. But it's one that almost everybody uses. So here's an example of a calculation on a cooling system. And normally we're not as worried about the COP on a cooling, but it can be done. And in this particular case here, we're showing a 3-ton heat pump that is delivering 36,000 BTUs of energy. And we're using the measured total input kilowatts, including the fan motor wattage of 4.8 kW of energy. So the 4.8 kW times the 3413, that calculation divided into the 36,000 BTUs is giving me roughly about a 2.2 coefficient of performance. There again, it's saying that we're getting 2.5 times the amount of energy that we're being able to transfer with respect to the amount of our capacity is very efficient. So it's a 2.2 is a decent number. But like I said, usually that's not something that we normally look at in cooling. It's more for heating. So in heating, the big thing is really it's coefficient performance has to kind of compare, is it worth it for me to run this heat pump compared to the alternative fuel source or the alternative system? And most systems aren't going to run anywhere near 200-300% efficient. So you're not going to get that out of a fossil fuel furnace. You're going to get maybe in the 90s or in the 80s, but you have to also look at the cost of the fuel is what has to be looked at. So in an example, in a similar type of a system, I might have a heat pump that's giving me a capacity of 33,480 BTUs, and the wattage going into it is 3.768 kilowatts of energy, and that includes the fan motor. So the total energy to produce that, if we take 3.768 times 3413 and divide that quantity into the 33,489, so it's BTUs output divided by BTUs in, is going to be roughly about 2.6. So that's telling me that I'm about 260% efficient. So that's a decent system. There is an additional factor that heat pumps have to also adhere to. So the government mandates that a heat pump uses, or that a heat pump has a heating seasonal performance factor that's figured into the application, and it's a ratio of your total seasonal heating or cooling energy that you're delivering during a period. And typically that's the way they rate them is they rate them over an entire season, but a person could calculate it in other time periods as well. So when you calculate it over a whole season, they call it a heating seasonal performance factor. So the performance factor alone is just associated with more. It's almost always associated with heating mode of a heat pump rather than looking at the cooling mode as well. So here's an example of some of the calcs. So in this case, the HSPF, or heating seasonal performance factor, we're going to look at the total BTUs of a heating system for a season, and we're gonna convert that or calculate that. What did you get for heating BTUs out of that season, and compare it to what was the total amount of power that you used to create that energy. And the total BTUs output divided by the total, in this case, the kilowatt hours per hour's input, that is we're showing 102,000 divided by 14,560. And of course, that gives us an HSPF of 7.0. And again, any system that's installed today has to meet a minimum standard, which is identified in one of your handouts that they do. And that obviously is subject to change as there's more requirements on a system. So this particular performance sheet or rating sheet is really useful for service, and this is really the only way that we're going to know what is the system going to perform to, how is it going to work, what are the efficiencies that I can expect out of it. So on the far left side in this particular manufacturer, which is showing me what looks like about a 3-ton type heat pump with a 3-ton air handler and a TXV, it's giving me the capacities in MBH. On the far left side, it's giving me the temperature rise, the kilowatts, the amperage. It's going to give me the coefficient of performance and energy efficiency ratio, and it'll give me some typical high pressure, low pressures that I would expect to get out of this system if I were diagnosing it or checking it out. And these are very helpful since heat pumps are difficult to charge in the heating mode. It's generally not recommended. So having this information is very helpful to help us determine if it's working correctly. So in my example, I'm just going to use a heat pump, and I'll use at 45 degrees. So at 45 degrees, it's showing me that I'm going to get 33,600 BTUs of energy out. That is the capacity that's going into the building. The temperature rise of the system would be roughly about 24.9 degrees. So that's one of the characteristics that's helpful in diagnosing a system is having approximately the correct temperature rise to know whether it's working as it should be. The amount of energy or kilowatts of energy being used to produce that 33,600 BTUs is roughly about 3.26 kilowatts of energy. Amperage, it'll pull about 14.3 amps. And of course, the coefficient of performance in this case is 2.86, meaning that it's 286% efficient in this case. Then EER in this example is coming up to 9.8. So high pressure gives you the typicals on this R410A system. Very, very helpful. Couple other things that I want to point out on this chart. You'll notice if I go down to 10 degrees, 0 degrees, if you look at the coefficient of performance, you're going to notice that the COP, even at 10 degrees, is still 2.0. 2.0 or 1.63 at 0 degrees. So you're still pretty efficient, but the dilemma that you run into is that you're not going to get enough capacity of heat out of it. So on a system like this where, and this would of course be an air source heat pump, the problem with this system is that as it gets colder outside and the building load is increasing, the capacity of the heat pump is actually decreasing, as you can tell. So that's really where the dilemma will fall and occur in an air source heat pump. So it is just what it is. So almost always this is one of the issues that we run into. Even at minus 10, we're still at a COP of 1.2, but the problem is we need a whole lot more energy or a whole lot more BTUs to provide heating sufficiently. So in this image or this picture, this is just showing some of the parts and pieces of a geothermal type of a heating system. And this is just something that's just slightly different. And on this particular geothermal heating and cooling system, it's showing kind of number 5 is showing me my filter application, shows the indoor evaporator coil, or indoor coil I should say, not evaporator coil. It shows a fan assembly. So a lot of the things you typically would see on any package system, we get as one really complete package. Controls, you name it. So let's take a look at the next one. So on this typical system, my fan motor, a lot of the geothermal type systems oftentimes are going to be an ECM type motor with a variable speed drive, and they may or may not have any electric heat as backup. The ones that we have at the college are indeed that way. The condensate pan is all going to be set up in there like any. So when we're in the cooling mode, we certainly need to have that. When we're in the heating mode, we don't need to have the condensate pan because there shouldn't be condensate there. When you'll notice a compressor, they may be single stage, they could be two stage, they could be variable speed. There's a lot of different ways that they could be doing this. And then of course they're going to have these top two are going to be something we're going to be looking at in a little bit, which is a de-superheater coaxial coil, and then the bottom two are actually going to be going for the loop field, or the, let's call it the source, or the for absorbing energy. For heating and for cooling, it will be the way you reject that energy, and that's typically how that would end up being. All right, so how does a geothermal kind of function and work compared to if I were to look at an air source. The biggest difference here is on a geothermal type system, the sun plays such an important role in the amount of energy that gets absorbed by the ground or by the earth. So all summer long, and what's happening is that the sun is providing heat into that particular earth, and so the ground is absorbing a significant amount. The ground acts like such an incredible buffer, so it's like a big battery that you're charging. You're allowing the sun to charge that ground up, and it will hold that ground energy, that heat energy. Now, the ground temperature stays very, very stable, which is one of the other advantages of geothermal over an air source system. So whereas an air source system, you'll see the temperature of the air change significantly with ambience on the outside, whereas for where the heat pump has to absorb heat, when you have a geothermal, it is very stable. In fact, you'll see very little changes in the ground temps if they're properly designed. So very helpful, very, very good. So it's one of the ways on these systems that you can really provide an efficient operating unit. It's by far the most efficient of all of the systems. So in what does the ground act like in winter? So the ground acts as the heat source in that winter. So in the winter, even though the ground is still 45 to 50 degrees in that area, it allows you to constantly pull from that energy source. And that's the key to using geothermal is allowing us to pull that energy and then give it to the indoor unit, where you could be dealing with a minus 20, minus 30 degree day in winter, whereas the ground is super stable. So that's kind of the way that works. So we use systems that pull heat and extract heat from the ground, and we try to give it to the indoor environment. In the summertime, you gotta have a place to get rid of the heat. So now we're gonna go the exact opposite. So since the ground in the summer, could be 45, 50 degrees as well, closer to 50 would be more appropriate, then we take the heat from in here and we send it back into the ground. So it's a way for us to reject it. That little bit of heat that we're putting into there isn't going to make a dent in the amount of heat that the ground has, but there's so much mass, it works very, very good. And again, if you're dealing with 95, 100 degree temps in the summertime, as long as your system has sufficient capacity, there's not going to be any problems with providing the energy, regardless of whatever this is going on in here. So from a heat pump or an air conditioner, when you're trying to reject energy, it's a lot easier to reject energy into a 45, 50 degree ground temps than it is to reject it into the 95, 100 degree temps outside. So it's just pure thermodynamics. So this particular image is showing an example of a system, and I'm going to point out a couple little things. This is kind of an example of a geothermal exchange system. In this particular system, we're going to take heat that's going to be in the ground in this particular case here, and what we're going to do is, in this heating application, we're going to grab water from the ground coming back in at roughly around 40 degrees on this closed loop system. And we're going to put that and pump it into my coax, okay? And we're going to have that water come back out and go right back into the earth. Now it's going to come out of this unit at about 32 degrees and go into the earth. It'll get warmed back up to the 40 degrees. And in that area, and it'll vary a little bit. So there are, if it's really, really, really high demand, this 32 degree water, depending on the length of runtime, it could be 32, it could be 30, it could be 25. If the system or the loop field is not designed correctly, you could easily see that 32 become 20 and 18. That would be an indicator that you got a problem if that's the case. So you don't typically want to see this temperature get too cold, or that's indicative of issues, whether it's flow rate, something that wouldn't be right. So we now have a way to pull heat out of it. The compressor is going to obviously move energy into the indoor coil, push that heat into the indoor coil, and it'll warm up that air coming from that building and send it back out into the building at, let's say, 98, 100 degree temps, depending on the capacity. And then, of course, that will be delivered throughout the system. Now, the heat pumps also have the ability to take the water using that de-superheater loop, and they can take some of that anywhere from 55 to 110 degree water, and bring it into a unit into a de-superheater coaxial coil, and it will then feed that and pump that right back into the unit. So it might come out of the unit and feed the unit at 110, 120 degrees. And it'll extract those BTUs, so it works pretty good on that. This system is, I'm just identifying as one that was identified at 450% efficient. So the COP would have been a 4.5, meaning $1 in gave me 4.5 BTUs of energy out. So $4.50 worth of energy out for paying for $1. So it's pretty impressive. Here's another system just showing a cooling application here, and you'll notice on here we're using terms again: indoor coil, outdoor coil. The indoor coil is going to remove the moisture, the heat from the building, and the heat pump compressor will move that refrigerant around the system, and of course reject or dump the heat out. So we might have water temps coming from the ground that could be, coming back at 70 and out at 80. And it's a way for us to reject that. So very, very efficient system. Typical applications for geothermal could be any forced air heating and cooling system. It certainly can be construction, new construction, a retrofit. Domestic hot water systems can do that. There are dedicated heat pump water heaters now that have been out for some time. Very, very efficient system. Radiant floor systems work quite well for geothermal. That's a huge application out in Colorado. They do a lot of in-floor heating. Works really, really well for that. Pool, spa, water systems, that's another way. Dual fuel systems, and then any residential commercial application will work. So this particular little heat pump system is showing a split system. So what they're doing here is they have inside this water furnace unit, they'll have a compressor and a coaxial coil with a de-superheater loop. So the de-superheater loop that's shown, or that would be shown here, let me change that. The de-superheater loop, that would be right there. That isn't hooked up right now in this image. This one here is essentially, let's call it liquid line, and that is your vapor line. And these two lines is shown for what they call a flow center. And there's basically they're using a couple of pumps, one of them to push the water in and the other one to pull the water out and push it back into the loop field. And so that's all done with your flexible lines. Typically they could be done with copper, but they sometimes they'll use, a lot of companies will end up using the flex lines on there. But nice, little split system. And then this would go to an air handler that's separate. So you can do it very similar to a normal conventional system. So we have some contractors in the Northwoods that actually do this a fair amount. So how does the domestic water loop kind of function and work? So here's an example of when the compressor is operating, it's going to send that hot gas directly into a small de-superheater coaxial coil. And it will provide, 110, 120 degree water coming out of there. typically not much more than that. So, and this is all driven basically by the expectation that the temperature of the refrigerant on the discharge line will be much warmer than 120 degrees. And that being said, those are B2s that you normally would have just lost completely. Now we don't need to do that. Now we can say, well, let's pull that heat out and put it back into your water for showering and doing all those types of things. The unit will send that hot gas directly to this indoor coil. This one's shown in a heating application. We're taking 70-degree room air and sending that out into 115 degree air going into the space. And then of course, again, depending on the mode of operation, the outdoor coil or the loop field will basically come back at 45 and it'll reject it at 32. And again, that's a very efficient way to use wasted energy, what would normally just go into the ground. So it makes a lot of sense. This one is showing a radiant floor heat on a water-to-water unit. So this GeoComfort unit that we're looking at is a water-to-water unit that has a de-superheater loop, and they're running, they can see they're running a flow center over here. They've got, they're providing a water heater in this application. They also happen to have, you'll notice all of this in-floor heating. So this unit is actually running all of the hot water right into this little tank, and then obviously we are heating and sending that energy right back into the loop field, so or back into the in-floor heating in this application. So again, very typical application for doing in-floor heating. A water-to-water unit will work quite well for that. In this example, in a dual fuel geo system option, again, where that split system was, it makes a lot of sense where a person could use a fossil fuel furnace, and as soon as the geo system doesn't have the capacity anymore, we switch it over just like we would in any air source. The only difference is that it's one or the other. That's primarily the main thing. So this is a very typical application in let's say in the colder climates, where we'll have a fossil fuel furnace as the secondary source, and then we'll use the geo for the first until you get down to the 25 degrees, 30 degrees in that typical. All right, so how do we do this? Well, typically we need to have some loops, some ground loops, or we need to have a way to pull heat out. And how do I extract that energy from the ground? So there's a couple of options. One of them is looking at it from a vertical loop. The other one would look at it from the horizontal loop. And in the vertical loops, what we simply just do is we come in with a drilling rig and just burrow down into the ground. So most of those rigs will go 150 to 200 feet deep for a system for every vertical loop. Now, so it's a good way to do it, but again, that's probably the most expensive of all the loops. The horizontal loop is another way where we can take, if we happen to have sufficient area, sufficient ground, sufficient areas that can be excavated, and you can then trench and bury these high density polyethylene pipes. You can bury them in the ground and then backfill them, and but you got to have sufficient area to do that in. The pond loop would be another option, and an open loop is the other one. So the pond loop, again, has to be big enough. They can take these loops, sink them into the water. As long as the water or the pond is deep enough and sufficiently and large enough, it's a very good system, and it will function fairly well. The open loop system would be the cheapest upfront, but it would likely end up being, as far as from an operational standpoint, you got to have a well that's dedicated just for that. Is normally how that works, and I'll talk more about that, about each of them coming up. So this first one, this is an example of a trench system, and what we're showing, obviously on the far left side, our earth is where the heat source is. That is what you're paying for, is that part of it. And on the far left side, they're showing a well drilling rig. In the middle and on the far right, we're showing two different loops. One of them is a slinky loop in the middle, and the other one would be just a normal, they ran a bunch of lines to and from, and that's their field. So that is their heat source in this application. So that's really what you're kind of paying for, is you're buying this fuel up front, or the heat up front, which is renewable. So it's one of the things that they end up doing. So heat exchanger options. Closed loops can be, they're obviously, these would be, any closed loop system is recirculated. So of those are the horizontal loop, the vertical loop, a pond loop, and then of course the one that is not done that way, that typically would be an open loop system, and that's considered as the pump and dump system. And so that's typically how that would end up working. So let's look at some of these. So the materials for these loop designs or loop systems. Ground loop piping, it's a very long-lasting plastic pipe, a high-density polyethylene material. All of those joints are fused together, so they will kind of almost plastic weld them. They use a heat joining method. It's a very, very reliable method. Just like any piping system in the ground, it can pull apart if its joint is weak, or if it became damaged somehow due to the elements. So, but typically that doesn't happen. Most of these loops also will have some sort of antifreeze or a brine glycol type solution. Most of them require something to be very environmentally safe, and there are a number of brands out there that do that. You have to have a small pumping station that doesn't consume a lot of energy, but it does consume some energy, and that's it's a part of the process. So, all right. So designing the loop. So residentially, you have to match what the load of the structure is to the equipment capacity. So you want to make sure that that's sufficiently sized, and that you're not oversizing one too much for one mode versus the other one. And this is something that is a problem on any type of heat pump system. The bigger the heat pump, the more heating capacity, but it also gives you more cooling capacity, and we may not necessarily want that. The proper depth and length is maintained throughout the heat exchanger. That has to be. So in other words, the loop field can't be 3-4 feet in some areas and 8 feet in other areas. So you want to try to maintain that. The design of the loop field is very important. You have to look at the moisture content, the soil type. So you have to have somebody that understands the ground and the type of soil you have to know how to design the loop field. So this is the one area that you definitely do not want to be skimping on, or you will run into problems with a geosystem not performing. So here's another loop field, a horizontal loop field, and in this particular one, we're showing a system that is showing a slinky on this part on the left side, and we're also showing just what they call a horizontal, a 4-pipe parallel loop on this one in the upper right. And those are, I would say, by far the least expensive, because it's just really just a little bit of excavating, and you run your pipes and run it back to the flow center. So it works pretty well on that. Here's an example of somebody that's backfilling at this point here. So it's just showing that application, nicely done. And this one's showing a slinky system. They've got, you have to have enough separation, and it has to be deep enough. So this one's most likely going to be approximately about 8 feet deep is what this one is. The vertical loop configuration. So typically, this one is showing, typical bores are 180 to 200 feet deep, which is very accurate. Requires, the least amount of area because you're going so deep, but it is also one of the more expensive. So every one of these vertical loops would be drilled down to a certain depth, and then what would happen is they would have that, whatever that ground is burrowed, what they would do is they would have to fill that with a grout. So what they do is they seal it with grout. So you're dropping the tube system down with a special 90-degree U or a U bend here, and on the very bottom. And then what they do is they fill this with a grout. So the whole pipe is actually buried in like a thermally conductive grout, and that allows us that allows for good conductivity to the ground, which is very necessary. What you don't want is air to act as your conductor, because that just doesn't work as well. So that's typical of what it would end up being on there. If you've got a multiple bore loop, which is more typical, almost always you're going to need at least one of those loops per ton. So in other words, if you have this one might be for a 3-ton loop type of a system. So if you had a 5-ton system, you'd need 5 to 6 of them. This is the one area, because of the cost, that sometimes to get people in on the deal, sometimes they'll skimp on it a little bit, and that's the one area you absolutely don't want to have that happen to. So here's another example of a system where they've got a pumping system that is showing some grout being pumped into the system. They've got their well drilling rig. This is one of the systems that they have to do on this particular job. So nice little rigged up setup. Another one here showing again the grout and their system that they're using on here. Again, this is just another way that they are setting up this rig. So the pond. So we can look at this one. This is by far the least expensive, especially if you don't have to dig the pond. But on this particular one here, you need to have a pond that's sufficiently large enough and deep enough, and so it has to be able to not freeze, completely. And that's the one thing that has to happen. So this is again another one of these where a person has to kind of design it properly, and talk to people that have experience on designing these things, and that would work pretty well on here. So, but there again, they'll bury it right into a pond. What some of the commercial jobs have done that I've had some knowledge of is they would have a retention pond where any of the overflow would occur for their systems, and they would use that as one of their mechanisms. So they dig a pond when they do the project, and then they bury their loop field in it, and then that ends up being a big energy saver for them. This one's showing a pond system where they're burying a slinky loop down into the water, and then so they'll float it out there, and then they'll drop it down is what they'll end up doing. This one's just showing some more slinky system, and they're building these up. This particular application here is showing me a vertical pump and dump system. So in this case, they have a well or a pump down in the well that's buried. They pump it out, they go into their system, and then they dump it out into another area that they don't really, they have no concerns about. So that's kind of one. This is by far, I would say, the least expensive of the systems, and you're going to have a little bit of energy associated with this pump and the operation of it, and you have to have sufficient water. You would never do this if you were buying the water from, let's say, a municipal supply or anything like that. So the open loop system is it's at least expensive up front. You are using anywhere from, most of these will run about 1.5 gallons a minute per ton as a general rule. You got to have enough area to get rid of the water, so typically that goes back into a pond, or it would go into the ground area, whatever it might be. And then obviously, maintenance, there's very little maintenance on those as well. There might be a little bit of periodic maintenance on the coaxials, but that is solely dependent on the type of water you have and how poor it is. This particular sheet is one of the sheets that we use to identify a geothermal system, like an analysis diagram. And on this one, very similar to the analyzing sheet that we had shown you earlier, is this one showing me, like a little worksheet that a person goes out and does service work on these. They would want to identify, your air temps in and out. He would want to identify what's the load coaxial. So it would either be this one or the air coil. So if it would be a water to water, you would have a coax on the load, and you wouldn't have an air coil. But if it is an air to water or a water to air type unit, then of course it would be we would have that as well. And then the source coax would be the one that we would be absorbing the heat from. So it depends on the cycle. So you'll notice also, they're identifying the compressors, so you can identify temps and pressures to identify superheats. They would look at discharge line temps, saturation pressures, superheat, subcooling. We'd be looking at all of these things. They also place, from a diagnostic standpoint, they place a lot of emphasis on temps and pressures. So your temps going in and out, and your pressures going in and out. And these would be, of course, on the water side or the fluid side for the source. So those are all, and then obviously water applications that said, in and out pressures, in and out temps. And they need to know those things. And we can take all of that information and we can plug it into some formulas to determine what the capacity is. So, for example, if I can, I'd have to identify my water flow rate or my fluid flow rate times either a factor and then times my delta T, and then I can essentially be able to diagnose the system from that and determine, is it performing up to capacity or is it not? So that's probably the biggest area. And if something isn't performing to capacity, then we look at all of your numbers and try to figure out, well, what isn't right or what's not working. And that's usually how we handle these types of systems. So, but that's essentially an analysis sheet.